Okay, so let's start. Welcome to this last seminar in the cycle and control structures. And we have the pleasure to welcome today Daan Leijen, who's a research scientist at Microsoft Research in Seattle, Edmond. So Daan is, has been promoting functional programming and type systems for a long time, first in the context of Haskell when he was an academic at Utrecht University,
Utrecht, yes.
And now in more applied context within Microsoft. And in particular, he's the author of the fastest malloc implementation in the world. But on his spare time, he also works on a very interesting language, Koka, which so it's a typed strict functional language that features effects and effects handlers and a interesting type system and a very interesting type-directed compilation to efficiency code. And so he's going to tell us a bit about the design and compilation of Koka. Thank you.
Great. Thank you so much for the introduction. Since I'm in Paris, of course, bienvenue tout le monde. Je suis honoré d'être ici aujourd'hui et faire une présentation lors d'un séminaire du célèbre Xavier Leroy. Merci beaucoup. Oh, thank you. But of course, I don't really speak French. Just what I learned at high school in the Netherlands. Yeah, but I'm very excited. I think this course is fantastic. And I've been working on algebraic effects for a long time in the context of the Koka language. And I give you a little overview before I kind of dive in. What Koka is, well, that's the logo. It's like Xavier said, strict language, and what sets it a bit apart is that it has effect types all throughout. So every function has an effect type as well, and it has full algebraic effect handlers. When I saw Mattia Pretnar and Gordon Plotkin present this, I was like, yes, this is it. So I implemented this, and this is what I'm going to talk about today. It has lots of other cool stuff, and I'm going to talk mostly about the first part here. So you see Koka goes to pure lambda calculus. And how do you do this? Because algebraic effect handlers have all this funny control going on. And I'm going to really dive in deep, like to say how we compile this rich algebraic effect handler language into pure lambda calculus, basically system F. Then there's another very interesting part about Koka, that is we don't use garbage collection, we use reference counting to do that. That's compiler guided, and I'm not going to talk about it today, but what makes it cool is that in the end we compile to C. So we don't need a runtime system or a garbage collector or funny tricks like root scanning, because just plain C with malloc and free. And that's partly the reason why we really wanted to compile algebraic effect handlers to pure lambda calculus, because we cannot manipulate the stack as such. So that's what I'm going to show you today, and a whole bunch about the design of algebraic effect handlers in a more practical setting. I also want to say a little thank you to all many of my former interns. We took this picture at ICFP 2 years ago. I see I have to work on my outfit. Maybe I should buy a new one. But otherwise, I'm very proud of all of them. They all become intern on Koka, and then they unfortunately leave me and become professor somewhere else. Like Ning Ning is now a professor in Toronto, and Wouter is a professor in Utrecht. Nikki Wazoo is a whole group at India. Jonathan is at Tübingen. So maybe after this talk, if you're interested in working on Koka and becoming a professor, maybe shoot me an email. So Koka, what makes it more special than many other languages is that every function in Koka has an effect type, and it's very strict about this. It's like you can't cheat it. So the best effect is no effect, total. So it will actually always terminate. It will not diverge. It won't raise exceptions. It has no side effects whatsoever. That would be like the square function. And you can see, so you have an input type int, an output type int, but also an effect type total. It's not a monad for the Haskellers. It's like really 3 different types there, but you write it with a space. But you can have errors, and maybe you have exceptions, or maybe you simulate a Turing machine and it may never terminate, or maybe you print, or now you do something with the console. You know, I don't know what that effect is. And you even have polymorphism over the effect. So if you have a map function, the map by itself intrinsically has no effect, but the function you pass in could have an effect. So it's like some effects E. And then map also has those effects, because it will apply those effects over the list. And why I really like this, and this is kind of before algebraic effects come in, and why I would, really wanted this, is that the type in Koka tells you something about the type of the semantic function. So if I would make a mathematical function that gives me semantics for each of these Koka functions, then if I would look at its mathematical type signature, it would be determined by the Koka signature. So if you have total, like no effect, then clearly you could mathematically model it as a 32-bit integers to 32-bit integers. But if there's an exception effect, well, now you get like mathematically something that would be going from a 32-bit integer to an integer or an exception, right? Or if you diverge, you go to like a richer set. It's either an integer or bottom. It never comes back. Like Haskell is always in this particular state. And in many real languages, like, I don't know, C# or something, well, now you also have a heap. So you don't just get an input int. Oh, you also have a heap. That's like the statefulness here. And you get back a new heap with updates. And you may have an exception. And it may not terminate. So this one is really hard to reason about, while these are easy, right? And this is kind of, I think this was the original motivation really to have this effect typing. And it turns out, I think in practice, a surprising lot is total in a big program, maybe like 70%. And then another 20% is just exceptions and divergence. I call that pure, that would be like Haskell. And then maybe 10% or 5% of your program is in this difficult part with I/O. At least that's the goal, right? Yeah, so I'll give a brief primer on the syntax, and then I'm going to show you how you use effects in Koka. So anonymous functions you write with this fn keyword. So here's like a while function with 2 arguments, like a predicate, anonymous predicate lambda and a body. And you can write it a little easier because you don't have to write the fn keyword if it's just, if it has no arguments. So you could just use braces. And functions, you don't even have to put parentheses around it. They can be trailing, so you can write it like this. And if you use indentation, you don't have to write those braces, just like in Haskell. So you can actually write, this thing. But it's all syntactic sugar. And this is maybe also something that's in Koka. It's like the minimal but general principle. So we use very minimal core language, which we can give good semantics and reason about, but we use syntactic sugar to have like a somewhat nice syntax that looks familiar, perhaps. But in the end, it's just function application. And I think what's interesting is you see here the braces. Conor McBride calls that the suspenders, right? So anything between the braces, it's a lambda, so it may be called 0 times or once or many times, right? While if it's between parentheses, it's evaluated before the call, like here, print hi, right? So I think that's kind of interesting. So I always feel that in many languages, this is of course parentheses around the while, but I would argue that that's wrong. It should have been suspenders. So one other funny thing, we have a with construct. It's really useful when programming with effects. So I'll show it here, but it's very light syntactic sugar. It kind of avoids writing these anonymous lambdas because you have many control structures that want like a function as a last argument. Well, you can write it like this. You write with, and then the actual body, you just follow it. So it saves you in parentheses. So if I have a function like twice, that calls f twice, you could write something like this, like with twice, print line hi, and it will like hopefully print it 4 times, right? So this last thing is equivalent to this. So you can read a width as like anything that follows is like an anonymous lambda that's passed in. And this happens surprisingly all the time with effect handlers, so you'll see width a lot. So try to remember this part. So actually, using effect handlers in Koka, I'm going to give a live presentation, which is always a very bad idea, but we'll see how well it goes. So here we are in VS Code, and here we see the twice function we just saw. And here was my example, right? Except now it's bonjour le monde. So let's run it. So I'll run, I'll do debug, and then here you'll see the output, right? So it ran it, and it says 4 times bonjour le monde, exactly. Good. So, and if you look here at the type, for example, twice, you see, for example, it has a console effect because I'm printing. All right. And if you look at twice, you see a very polymorphic type. It says, for all alpha and effects E, give me a function like with an effect E and a result alpha, and I'll have an effect E and a result alpha. So I only call F twice, right? So how do you make your own effects? Well, you can define an effect declaration. And you can say I have a new effect called exception, EXC, and it has one operation called raise, which is a control operation because it can capture resumption. And you'll give it a message. Oh, I shouldn't hover, right? You give it a message and it returns an int. So I can already, when I declare this, I have a signature. I don't have an implementation of raise yet, but I can already use it. So I can write the save division function over here. And it says if y is not 0, I do a division, but otherwise I call this raise operation. And because I have the type signature, I can call it. I don't know yet how it's going to be implemented. And I say divide by 0. So now you see in the type signature that the exception effect is there, right? Because we call raise. And now you can define a handler for that raise. So if some computation like savediff that could cause exceptions, well, how would you handle it? So the handler expression lets you define an implementation for raise. And here the only thing we're doing is we print the message and then we return a unit immediately. So if raise is called, it's just like an exception. It goes up until the handler, and then it prints the message and then exit with a unit. So if you look here, for example, 1, and here, of course, so handler itself is a function because it takes an action that you're going to execute in this context over which you're going to handle the effects. And in this case, we call save div, right? Which will maybe call raise. It will, because we pass 0 as the second argument. And if you look here, it's interesting because save div has an exception effect, EXC, but example 1, we've handled it, right? But we also introduced a new effect that we cause, named because now we're printing to the console. So you can, like with handlers, you can kind of transform your effects. Yes, if you run this, it will say divide by 0, as you can see here, because it will print it. Now this is not great syntax, right? Like a handler, indeed, it becomes a function that takes one of these actions. But you can already see this is just what width is for, right? So we can write it a little nicer like this. So now the handler expression is a function that still expects the action. Well, that's now the rest of the program, right? And we even let you write it a little nicer. Like if it's just one function, you can just write this. And I think this maybe already give the intuition that algebraic effect handlers are much like dynamic binding. We're going to kind of say like, well, in the rest of this computation, raise means this, right? And the effect types track that we actually have defined all the things we're going to dynamically call. So Eric Meyer always said, who used to be my supervisor in Utrecht, always said, dynamic binding, but with static typing. Right? We don't want to forget to bind any of those. So that's an important part here. Let me see. Instead of printing a message, we could do other things, right? So here I say, well, if you raise something, I will return nothing. This is the maybe type in Haskell. And otherwise, we return just. So now we convert from exceptions to a total function, to maybe type. All right, and that's something we can always do. And I think I wrote it a little nicer. Well, later, right. So here you can do this a little nicer. So here we apply this just at the results, but you can actually write it like this. So you can now completely abstract. So you can say handle raise by being nothing, and if a normal value comes back with the result of save diff, then apply return x. So the x would be the result of save diff, and then we wrap it in just. So now it's nicely contained within the handler, and return is like a special clause in that. And then we can actually a little bit abstract away a bit from that, right? So we could actually write a toMaybe function that for any action that has an exception effect and maybe more effects, this is a row type, there's a polymorphic tail, like more effects E, it will handle the exception effect and convert the result alpha into a maybe of alpha. And then only the effects E, all the other effects are left. And yeah, here you see, right? You do with handler and you package it up, and then you call the action. And then, of course, you can use that itself with a with. So you can write with toMaybe, it handles exceptions. I will execute this. So if you run this, the answer will be nothing, right? Because I divided by 0. Or if I would type 2 here, the answer will be, let's see, just 22. Is that right? Yes, good. So a nice thing here, I think what shows here, often you see these discussions on Hacker News and stuff like, oh, should we have maybe types or option types, or should we have exceptions? But in a way, it's a fake discussion, right? They're isomorphic. You can take exceptions, convert them into the data type, or take the maybe type and convert it into an exception, right? So it really depends on the pattern. What do you want to do? If you're all the time looking at the results, maybe you should use a maybe type. But if you want to abstract away from something that goes wrong, maybe you should use an exception, right? But there's no fundamental difference, as you can see here. Oh, I already had the, well, there we go. Let me see. So the real power of effects. Right now, it's just been exceptions where we throw. But of course, you really want to resume things, right? As we've learned during the course. So here is two of those example programs. So here, in the first one, when I say raise, and you know, it catches the raise that's called in save diff, we'll just return with 0 as the final result. So if I run it, save diff will be called, it will call raise, it will jump all the way up here, and then just return 0. And the final result will be like 0. But what I could also do, and it's maybe also a valid way, is saying, well, if someone calls raise, go back to where you were called and give 0 as the result. Right? So I would come back here now, and instead of exiting here, I resume here, but now it's 0. So save diff would return 0. Let me, where am I? Yeah. So if you run this, it's 1, right? Because save diff will be 0, and we add 1 to it. So now we've resumed. And this really unlocks the real power, and it's why we call this control, right? And a nice illustration is always the reader effect. Sorry, yep.
Can you apply resume of 0?
Resume of 0. Yes, in this case, because the result of this action is an integer. So you would, let me do it. Why not? Well, I will regret it. I know already. Let me see. All right. Well, type checks. So let's go run it. 2. Now think carefully if that's right. I do think that's right, actually. Let me see. Yes, because we resume with 1 the next time around. Right, and then it's Again, +1, and then it's 3. If you understand this, you really understand algebraic effect handlers, how they work. That's great.
So that's a multi-shot, right? What happened here is a multi-shot continuation.
It's a multi-shot continuation, yes. There was actually, I was still saving that, but the audience is ahead of me. I need to go quicker. That's what you get with great teachers. So, yeah, I'll just keep going. So ask returns an int. You can call ask, it gives you an int, right? This is actually, here's of course silly example, but in general you see, for example, in JavaScript they have these express frameworks for HTTP servers, and then they always pass down the current connection. Because you have, you know, 1,000 strands that have connections, and they pass it as local variables. How nice would it be if you could ask for the current connection, right? Instead of manually passing it down. So now I can make an ask diff that says, oh, give me an X, give me a Y, and then I do save division on it. And I can already write this, right, without having any implementation yet. And you see that ask diff has both ask and exception, because save diff uses the exception effect. So now I can run that, right? So I can say, well, just always give a 1 back, right? So always resume with 1. And we still have to handle our exceptions. So example 3a is a pure function again, how we like it. So you can run this, it will be 2, I guess. Just 2, yes, no, nothing goes wrong. And this happens, so it's a little silly here in the example, but I want to say that this happens a lot. It's a function that the last thing it does is resuming. And I call it a stale resumptive, and I come back to that, if I'm fast enough, how you can compile those efficiently. So in Koka, you can actually write them, instead of saying control, you call them function. And you don't have to say resume, you can just say, oops, 1. Because it's like a function that just returns 1, and you can see it as a dynamically bound function. It doesn't change your control flow, right? And I think that's also very nice for reasoning, when you know for sure, if it's still resumptive, it won't mess with the control flow. It will be like a linear flow if you have such operations. Actually, I'm going to go a little faster. Here's an interesting one. Every time you ask, you get a little bigger number. First it's 1, and then it's 2, and then it's 3. And in the end, I will also return you like the count of all asks, right? Actually +1, I guess, because I just call ask here. So it returns 2 things, like the result, but also the count. So if I run that here, so we convert the exceptions to just, and then we have this ask int binder, which is one more, but in the end also tells you how many times it called ask. So if I run that, it says, well, just 1 is the result, because we first got 1 and then 2, and if you divide that, that's 0. So +1 is 1. But we called ask 3 times, because I also call it in the end 1 more time, right? And here you see the typing gets important, because this result is a maybe of int, because I handle the exception here. And then I handle the ask, which tells me also the final amount of asks, right? So it's a tuple. But if I turn the handlers around, then first I create this tuple, and then I make it a maybe or not, right? So if I run this one, you get a just of 1 and 3. And it's actually really important, because one of them is kind of like a transactional memory. It says that you only get the final int, like how many times you called ask, if there wasn't an exception. But here, whether it's an exception or not, once that happened, you get also the final count of the number of asks. And that's more like how normal exceptions work. Because if you write something in the heap, you keep that value when the exception happens, right? Well, this is more like transactional. So the order of the handlers determines your semantics. So a beautiful thing about algebraic effects is that they're compositional. You can just write these handlers in any order. But it's also very important. It changes fundamentally some semantics. And this is also why I feel typing is very important. Because if you don't have types, it gets hard to figure out what the result is you would get out of here. And the time goes so quick. Well, I'll go quickly through these because I think there were not too many examples with multiple resumptions. So here's one fun example about that. So I have a non-deterministic effect, and I can either flip, which gives me a Boolean, or fail, which is for any alpha, right? Because it's going to be like an exception. And then I can write a function that selects randomly, or non-deterministically, I should say, an element from a list. So if the list is empty, I fail. And if it's a const, I flip the coin, and then either I return the head element, or I just keep looking if it's false. All right? And then I can solve the knapsack problem. So if I still have weight amount left, I have a bunch of items of certain weights. Can I make a list which add up to the weight, the knapsack problem? So I have cheese and wine and a baguette, right? So if weights 1, 2, and 3, and I want to fit it in my knapsack. So if the weight's already like too much, like it's you become negative, you fail. If it's 0, you exactly packed your knapsack, so then it's you have an empty list. But otherwise, you just select an item non-deterministically with this flip stuff, and you add that to your result list, and then you look, maybe I can still find more items, right, to put in there. Although you could fail in the end. And then here's a way to get all solutions. So if you return with a value, you say, okay, well then that's at least one solution, so I'll put it in a list. If I fail anywhere, like if I ever get here, I try to jam too much, I'm going to just bail out completely and give an empty list back. But if I flip, I first try, true, which could result in a singleton list or this empty one. But then I append all the results for false as well. And because flip gets called like nested, you get all solutions in the end. So here is what was it? The baguette, the wine, and the cheese. And my knapsack only fits 3, something of weight 3. So if I run it, you get all solutions, like 3, 2 and 1, 1 and 2, 1, 1, 1. And this is very cool about multiple resumptions, that you have this nested behavior where you can keep doing very interesting things. And here's, I think, the compositionality and orthogonality. I define this once, I just says it's non-deterministic. And you see its result is a list of things in the knapsack, but then solutions makes that a list again, right? So this, in the end you get a list of lists. But I could also do it eagerly, like through a maybe. And that's completely orthogonal. I could also say, well, instead of all solutions, I try the first one. So return is just, fail is nothing. And otherwise, I first resume it true. And if I have a solution, haha, I'm done. But if not, I'll try again with false, right? So now I just use a different handler, but the same code, the same algorithm, and now I get a just 3, right? That's cool. Yes, and there's many more things. Asynchronous programming is a big one, which I won't show today. But basically what you would do with async programming is when someone does something asynchronous, you capture the resumption, you store it, and when the async operation comes back, you resume. Right? So it fits really, really nicely. So that was Koka for today. Now I'm going to go talk about like the real semantics and how we compile this in Koka. And I hope I get all through it. So semantics of handlers, right? I think there's a bunch of there's still the original paper by Gordon Plotkin and Mattia Pretnar where they give a category theory interpretation of what effects and handlers are. It's still very beautiful, right? Where handlers are essentially folds over your free monad. And actually, I would say the thesis of Mattia is very readable and very nice. So I would say anyone, please read it. And he was here, of course, last week, where you could, hear it from the master. So I'll give a much more, first maybe more runtime-oriented intuition, and that's because in the end I want to like compile to C, so I want to kind of show you how it would work at runtime versus in math, right? So when you have some handler, H, that's on the stack, and you do a bunch of calls like save div, and then at some point you call raise, and usually you write that more formally with the perform, you perform a raise. You want to kind of go up the stack to find your handler, and then execute whatever operation you defined. So you unwind your stack, it becomes empty, and now you continue with the operation, with the value that was passed to you, but also you capture the resumption, right? And that's basically, you copy the piece of stack here, you put it in the heap, you leave a hole at the end, so you can later resume with the result. But it's, this is of course expensive business, copying to the heap. And you also need to kind of control your stack to be able to even copy it, to know like all the frames, right? And with exception handling, it's a little simpler in most languages because there you don't capture this part. You don't need the resumption, right? You just unwind. So here's an example with ask. More concretely, right? You would when ask is done, you unwind the stack until you find your ask handler, and then you pass the resumption as it was done. And then when you execute ask, you just call the magical resume with 1. So now you copy the whole thing back again on the stack, but with 1, and now you continue from there, right? And this is tricky to compile well in a language. I want to take one step back to kind of the mathematics. I personally really like thinking about algebraic effects in terms of an operational semantics. I would everyone actually also recommend to read a fairly old paper by now. What is it? 30 years old, but it's still beautiful. Syntactic approach to type soundness, where Matthias Velleisen and Andrew Wright introduce evaluation context and how you can very concisely specify evaluation. And if you do that, you get these transition rules. And it turns out for the lambda calculus, there's just one, that's the first one, that's just beta reduction. Well, it can't be any more beautiful than that. One evaluation rule, right, to rule them all. But with handlers, you get a few more. But I would say, once you have this, you can do all effects, right? You do exceptions, you do async, you do all these other things. And you don't get a funny collection of effects baked in, as is common in most languages. Of course, Camel 5 is beautiful again. So here we have the, so if you have a handler expression, like in Koka, it would still get the action, right? But it would install a handle frame with the handler and then execute the action. And then the handle frame says, well, if you ever return normally with the result, you just pop the frame and you return the result. And this is the interesting one with the perform, and this is the one that's hard, right? So what you see here, we perform an operation that's handled by some handle frame, but there's this whole context in between, this big E. It's like all those frames in between, the whole piece of stack plus the registers, essentially. But very concisely written. That's why we like math, right? And you see here this side condition that says there shouldn't be a handler in between that handles this operation, right? H must be the first one. You always go to the innermost one. And then you capture that whole evaluation context, right? The resumption is a lambda that restores the whole thing and it plugs in the whole. And this is exactly the difficult and expensive part, like capturing this whole context. So how do you go about that? Well, I would say we have a cool paper on this, like how to do generalized evidence passing, and I'm going to explain that to you today. But there's also other ways. No, I skipped ahead. Okay, well, this is what I'm going to talk to you about today. How do we translate these three like fancy rules into just pure lambda calculus again, like system F. So we have only one, just the application again, so in a pure calculi. And that requires a whole bunch of steps, which I'm going to talk about. I want to take one step back. So when you have a general perform, there could be all kinds of handlers on the stack in between. So generally, you kind of like, you search and you're like, no, this handler is not good. This one's not good. This one is going to handle my things, right? And that's kind of that side condition here that says find the innermost one. And then you capture. So then you grab the whole stack and you captured it and you continue with whatever the definition is. And how can you do this efficiently? That's the question, because if you just unwind, now you would have to copy the whole stack that's full into the heap, and then you can continue on the stack with the current operation. Well, you can do a trick. So Camel 5 is an amazing trick. They implement a runtime system where you have split stacks. So what you do is every time you create a handler, you create, so you're executing here and then a handler happens. Well, then you create a new stack and a nice small stack, right? 4K, you allocate it. But you link these stacks together and you start a new handler. And as soon as you find another handle, you create a new stack. And now you get this split stacks, they call it, I think. In the end, you do perform. But now you have all these little stacks that are just around. And now when the perform happens, you're going to search through your stack segments until you find the handler. And then you're like, now I want to continue. But now you can continue right here because that stack still has space, right? It's still there. And the capturing, you don't have to copy anything. You just point to the rest of that stack segment, all right? So that's really smart. Now you don't have to copy your stack. You don't have to reallocate it. So you still search linearly for the handler, but you have a constant time capture. And if you only allow one-shot resumptions, then it's also really quick to resume, right? You don't have to copy this entire series of stacks, the resumption. You can just immediately like continue here with the result value. And then it starts evaluating again, and that's why you can only resume once. There's more cost. Like it's not just free, right? You also once you have split stacks, you still need to grow the stack even in regular code. So there's lots of other things you need to do. For us, though, or for me, a problem is it requires a special runtime. And I'm at Microsoft Research. I really would like to use my language in certain scenarios. We really want to compile down to C or say WASM, right? So this solution doesn't work there because we don't have these stacks in C and I can't look at it. And in WebAssembly, I can completely not look at it. And that's where we did this research to get algebraic effect handlers directly to pure lambda calculus. I'm going to show that now, and maybe I'm going to go a little fast because I think I have like only about 10, 12 minutes. So how we do it is a series of steps. So we're gonna use multi-prompt delimited control. We're gonna use evidence passing, a monadic translation, and yield bubbling. And then we end up here. And then it turns out if you do a little monadic inlining, you get good C code out. And I'm going to show you how this works, all these little steps. So the first step we're going to do is we're going to separate out with handling and performing. You first look for the operation and then you yield to it, right? I want to separate these two things, the finding and the capturing. So fortunately, here at INRIA, Didier Remy and others already thought about these kind of control structures almost 20 years, more than 25 years ago? I can't calculate anymore. 28 years ago. 29, wow. And they had a really nice paper about multi-prompt delimited control. And that's, I think, a very good primitive to implement algebraic effects. I've been arguing that WebAssembly should have this, but I lost. We have something else, also very nice. But the nice thing about multi-prompt versus shift reset or call CC is that you can give it very simple types, which I really enjoy. So you can install a prompt on the stack, and you get a marker for it. Could be like a unique number maybe, but it's typed. It says the type of this point in the evaluation is alpha. Often you call that the answer type. And you give it an action that gets this marker, and of course has that result type, right? The answer type. And then the whole thing is that answer type. And then later, when you want to yield to some marker, you know the type of where you're going to yield to. So you don't need a more complicated type system with answer types in your derivation rules. It's like just Hindley-Milner types. And then you pass it a function that's going to execute at that marker in the answer context. And it gets a resumption function that if you give it the final result to resume, B, right, it should go also to the answer type A. That is nice. So first we're going to translate handlers using mprompt and yield. So instead of handle H, we're going to be multi-prompt M, right, H. And then I can just yield to M. I don't have to search through the handlers. Well, I still have to search, but I just go to M. It will be unique. There won't be like an innermost or something. And then I can just capture that, right? So this is basically just the capturing part of algebraic effect handlers. And then what are you going to execute? Well, the yield is going to give you a function, right, that takes the continuation, the resumption, and execute it. So in this case, we will do ask, and we pass it the resumption with the mprompt in it, right? And then once ask resumes, you'll get exactly the right thing again. So this is good, except how do I know which M I have to yield to? And how did I even know like what the implementation of ask is, right? So what we do there is we're going to pass down evidence for all handlers down the stack and use mprompts up there. So we remove the searching. And that's called evidence passing. So when we do a computation, we continuously maintain an implicit EXA parameter. It's called the evidence vector. So if we have a handler up there for ask, say, right, then all of those become just mprompts with unique M's for the markers. But I also have an evidence vector. So initially it's empty. But then in that part, there is actually a handler. So it says, well, effect 1 has marker 1 with handler 1. And this contains all the implementation, including the ask. And the evidence vector gets bigger and bigger. There's like an effect 2. Oh, there's an effect 3. It basically, the vector is a mini stack that only contains the handler implementations. And then when I'm here with the perform, now I see like, well, the operation belongs to effect 1. So I yield to M1. And H1, I'll just select the operation out of it. There will be ask in this particular case, right? And that's what I'm going to yield with. And now I've separated out kind of the determining what operation to do and which one, like how to find it, from yielding and resuming, right? So we have the multi-prompt delimited control plus the evidence vector that gets passed down. And the nice thing is that now if you look in the operational semantics, I don't show that here, but now it's completely local. Like there's no context that I have to look through. It can be locally decided, and you just select the operation from your handler record, which works out really well. And types for the win, right? I just learned from my son that FTW is for the win. So I was like, types for the win. So there's two things you could do with these evidence vectors. Like here, I ordered them kind of according to the stack, or maybe in reverse order, I guess. Well, you can do a little better. If you order your effects like in a lexical order, and you have types, right? Then if I have a function like foo with 3 effects, and it's a closed row, I know that the evidence vector at runtime that's going to be passed to VU is 3-element vector. And if I order it lexically, I know that the first element will be the console handler, the second element will be echo, and the third element will be exception. And that's really nice, because now I can do constant indexing, right? If I call, why do you use echo? Maybe ask or something. If I call echo or ask, I know, oh, it's right there. It's the second element of the vector. I don't have to search for it, right? And this is really powerful. And you can even do this, and it's too advanced. I should actually skip this slide. But you can even do it with polymorphic rows. If I don't know it is more effects, E, it's polymorphic, then I don't know. It's maybe a very big vector. I just know that console and action will be in it. Well, I can secretly pass kind of constraints, like how would you insert console into E, or how would you insert exception into E? And then at runtime, when I instantiate things, I actually call it at some point, like say here with bar, then I know what offsets are required. This is much like the typed record extensions in Haskell that Mark Jones once did with Benedict Custer. A very beautiful paper. And then you can pass those integers as extra arguments at runtime, because you can always resolve these predicates. Koka is not doing this right now, so if you're a PC student and you want something cool in between types and runtimes, it's open. Evidence passing for the win, right? So now we have this constant indexing. So when I'm down here and I do perform the operation, and suppose it's ask, right? And I have one of these fun things, right? Where I know the last thing is the tail resumption. I talked about this before. Well, do I really have to yield up all the way, and then resume with the 1 all the way down again? Maybe I can avoid it. Let's not yield at all. You know what? I'm just going to do it right here on the stack. Because I know the last thing it does is resuming. I can just execute ask like right here where I am, like in place. And that gets really efficient, right? Because now we can locally select the implementation from the handler, because we did the evidence passing. It's right available here. So we can just immediately call it with the value and no resumption whatsoever, because we had declared it as fun. So sometimes we know this statically, but we also set a flag. So we can also dynamically see whether it's one of these tail resumptive operations. And there's a little, this really reminds me of virtual method calls, right? We can statically select in the evidence vector which evidence, because we know it by the types, and then we select the right operation and we just call it. So it's almost like object-oriented programming. There's a little thingy that's subtle. The operation itself could still call other operations, and then you want to find the right handlers, not these ones that were in between, right? So you actually need an extra frame here where you change the evidence vector to be the right one, as if you've been executing it up there. Oh, I don't know why. Right, so 5 more minutes, I can do it. So we're almost there. So the last thing we do is called yield bubbling. So suppose we don't have these, by the way, there's many of operations that are tail resumptive. So it's a huge win to make those fast. And I think even if you have split stacks, you can also do more these kind of things. So I think it's something that anyone should consider. But in general, you can of course yield. And capturing the stack, I can't do that in C. I can't like look at the stack and change it, at least if I want to have portable C. But what I could do is like unwind one step at a time, right? So when you yield, I start with like an empty continuation, and then slowly I'll just build up a bigger and bigger continuation, unwinding all the frames until I match. I get to the right marker, M1, M1. And then I'm gonna execute it, right? Then I have the whole thing. And this unwinding, how can I do it? Well, I can make a monad, a control monad that either is pure or you're starting to yield up, right? And now with the monads, you can make all your continuations explicit. And this is really the monade libre. But I have only, instead of all operations that you would normally do in algebraic effect handlers, you would have a constructor for each operation. I'll just have one, because this one can rule them all, right? This is the multi-prompt delimited control. And it's enough to do everything, because you're passing in like what you're going to execute at the end, right? This is actually a really interesting type, very beautiful, and I don't think I have enough time to explain it, but the nice thing is you're going to yield to some particular marker, which is in some answer context, with some answer effect. While your continuation is still the monad you're building up. So while you're bubbling up, this E and A changes and changes until you hit the right marker. And at that time, you know that the answer type will match the alpha prime here. And that's kind of a dependently typed operation. So we have a beautiful Haskell library where we use like a slight dependent typing with a refl, reflecting, that proves that those types at that point become the same. And then you can type everything very nicely using DADTs. And then the final monad is a combination, right? It's something that takes implicitly an evidence vector that corresponds to the effect type, and you're in a delimited control monad. And that's the entire monad. And then you can write, you can translate a program, like ask plus ask, into explicitly bind operations of the monad, and now every continuation becomes explicit. And that's the trick, right? Now I don't have to look at the stack and see. All continuation points are explicit. And the bind is really elegant too. Like you check if it's normal, pure, you just keep going, or if we're yielding, and then we keep yielding, right? And the nice thing is that every continuation now, we can actually save it as a, and this is Kleisli composition, which also works out so nice. Oh. But we do one more trick. We inline all those binds. So that's very, very important. So here these functions would be really expensive to allocate lambdas all the time, right? So, but if I inline them, most of the time, I will just be pure, especially for ask. It doesn't even yield, right? So just pure, and now I don't allocate anything, and I have a very good, happy, fast path. Only if, you know, if you have an expensive yield, now we need to actually maybe allocate a lambda at that point, right? So kind of opposite to the earlier talk by Andrew Kennedy, which is wonderful, I say, no, compile without continuations, right? Because you could also do this completely continuation style, where you pass immediately the continuation to ask, but now you can't look at the results. You're forced to allocate this lambda. But if you do it with a bind, you get results back on which you can match and like delay the allocation of the lambda to only do it if it's truly needed. This is of course quite different than Andrew's talk, which was really about doing an optimizing compilation with continuation. So yes, you should still do that. But for this part, you shouldn't, right? Monads help you do this. And then once you do this, now you can make kind of efficient C code. So this is actually what Koka will generate. Like once you have this pure lambda calculus, you do this nice inlining of the binds, you can kind of see how you can make a fast path with like here's the perform of the ask, that would be the ask, and it selects from the local context, it's always passed around, like the 0th element, because we know the type, so we know it's there. And then here's the check, we kind of build the monad in, we set a special flag in the thread local context. And normally this is not true, so we put it in an unlikely branch, so the compiler moves the code for yielding like to the end. So the actual assembly code is perform ask, and do it, with 2 tests in between, right? And generally this works out quite well, right? You have to be very careful though about code explosion. I didn't go into it here, but the paper tells you those things. This paper tells you a lot about this. Right. Thank you so much. I hope you found it interesting. Please try out Koka, and thank you so much.